So this is electromagnetic fields and waveguides. This is the lecture session, and in today's class we'll discuss about rectangular and circular cavity resonators. Okay, so this is especially for you, my students and young researchers, and you can reach me at dr.christoananth@gmail.com. So before beginning the session, once again let me thank God for giving me this opportunity to deliver this useful session to share my knowledge among my fellow national, international participants, students and young researchers. So in this class, we'll have a short introduction towards resonator. What are the performance parameters, the characteristics of microwave resonator? What are cavity resonators? Then the operation of cavity resonators. Then we'll discuss about reentrant cavity resonators. Okay, so then we'll discuss about the equivalent LCR circuit. Okay, inductance, capacitance, resistance circuit. Then the dominant mode of the rectangular resonator, the dominant mode of the circular cylindrical cavity, and what are the applications which are associated. Okay, then we'll understand the coupling of the cavity to the electron beam. So we'll also understand the pulse repetition rate and the tuning of the cavities. Okay, so at regular intervals I'll be giving you some short videos to discuss the knowledge in our topics. Right. So resonator, it's actually a tuned circuit which is going to resonate at a particular frequency. Here the energy stored in the electric field would be equal to the energy stored in the magnetic field. So that's resonation. Okay, right. So resonant frequency of the microwave resonator is the frequency at which the energy in the resonator is going to achieve a maximum value. So that would be like twice the electric energy or maybe twice the magnetic energy. Okay. So maybe at low frequencies, maybe like up to very high frequencies, up to like 300 megahertz. So the resonator will be having reactive elements or maybe like lumped elements like the capacitance and the inductance. Okay, so the inductance and capacitance value will be very, very small. Okay, because the frequency is increased beyond the very high frequency range, and therefore it is much more difficult to realize. Okay, so here we will be using transmission line resonator using the distributed elements like the sections of the coaxial lines. Okay, so coaxial lines, either it can be open or it can be shunted. Shunted means it will be parallel. Okay, so open or maybe shunted at the end section. So that will be confining the electromagnetic energy within the section, and here it will be behaving it as a resonant circuit having the natural resonant frequency. So at maybe high frequencies, the transmission line resonator does not give very high Q factor, quality factor, due to the skin effect and radiation loss. So the transmission line resonator is not used as the microwave resonator. Okay, so we'll understand the performance parameters of the microwave resonator. One, resonant frequency, that is F suffix R. Okay, and then quality factor Q, and input impedance ZIN. Okay, so quality factor. So quality factor is nothing but the measure of the frequency selectivity of the resonator. So Q factor, Q can be given as 2 multiplied by maximum energy stored divided by energy dissipated per cycle. So it can be like W divided by P. Okay, so that is the maximum energy stored per the energy dissipated per cycle. So W is nothing but the maximum stored energy. P is nothing but the power loss, the average power loss. Okay, and we have some methods for constructing a resonator. So the resonators are built by using lumped elements like inductance and capacitance, using distributed elements like the sections of the coaxial lines, and using rectangular or maybe circular waveguide. Okay, then we'll understand about cavity resonators. So it's actually a piece of waveguide closed at both the ends with the metallic planes. Okay, so here the propagation in the longitudinal direction takes place in the waveguide. Here standing waves is going to exist in the resonator, and oscillation can take place if the resonator is suitably excited. Okay, so several aspects of the cavity resonators can be considered. So waveguides are used at highest frequencies in order to transmit power and signals. So similarly, cavity resonators, you can employ it as tuned circuits at such frequencies. Okay, so the operation is directly related to that what we try to operate with the waveguides. Okay, so until now, waveguides has been used, okay, especially for picturizing the standing waves, okay, and traveling waves in the longitudinal direction. So maybe if the conducting end walls are maybe placed in the waveguide, so then the standing waves or maybe oscillations will take place if the source is located between the walls. Okay, so that will be the distance between the end walls to be n lambda p by 2. So this n is nothing but any positive integer. Okay, so this is the transformation from the rectangular waveguides propagating TE10 mode to the cavity resonator oscillating in the TE101 mode and TE102 mode. So this is the short circuiting end wall, okay, and this is the suitable position for the second wall. Okay, so we see that in a slightly different context of the placement of the first wall, that will be having standing waves, okay, and placement of the second wall will be having oscillations. Okay, so that the second wall is placed such that the pattern due to the first wall is left undisturbed. So if the second wall, maybe if it is lambda p by 2 away from the first, okay, so oscillations will take place between the two walls. Okay, so it will all continue until all the applied energy is dissipated or indefinitely if energy is constantly supplied. Okay, so that's same to the behavior what you see in the LC tuned circuit. Okay, so which means that any space enclosed by the conducting walls must have one or maybe more frequency at which the conditions are fulfilled. Okay, right. So in other words, you can say any such enclosed space must have at least one F suffix R resonant frequency. So the completely enclosed waveguide has become the cavity resonator with its own system of modes, okay, and therefore the resonant frequencies take place. Okay, so we have both the transverse electric as well as transverse magnetic mode numbering system, so that is going to break down unless the cavity will be having a simple shape, and definitely you can think about having a resonant frequency rather than the mode. Okay, so this is the diagram we will have with the reentrant cavity resonator. So here every cavity resonator will be having infinite number of FR resonant frequency. So that is how you try to consider with the resonator of the oscillations to be twice that of the frequency, because every distance, that distance between the walls would be lambda p. Okay, earlier case we had lambda p by 2, now we have lambda p. Okay, so several other resonant frequency series will also be present, so based on the other modes of propagation. So there we will have the oscillations which take place within the cavity. Okay, so this behavior is not really required or naturally wanted in the case of the resonator, because that these things will definitely make the device harmful. Okay, so the cavity can oscillate in several frequencies, does not that it will resonate all the time. Okay, so such frequencies are not generated spontaneously, but they must be fed in. Okay, so there are two types of cavity resonators. One is rectangular and circular. Okay, so rectangular or maybe circular cavities, you can use it in the microwave resonators because they will be having the natural resonant frequencies, and it will be behaving like a LCR circuit: inductance, capacitance, resistance. Okay, so cavity resonator can be represented by a LCR circuit, and the electromagnetic energy which is stored in the entire volume of the cavity in the form of the electric as well as magnetic field. Okay, so the electric field, the presence of the electric field will give rise to capacitance value, and magnetic field will give rise to inductance value. Okay, and there will be the finite conductivity in the walls which gives rise to losses. Okay, so that is across the walls, that will give a rise in the resistance value. Right, so the cavity resonator, you behave it as a equivalent LCR circuit and will be having natural resonant frequency. So cavity resonators are formed by placing perfectly conducting sheets on a rectangular or maybe a circular waveguide on the two end sections, and all of the sides are surrounded by conducting walls which forms a cavity. Okay, so the electromagnetic energy is confined within the metallic enclosure and they will be acting as resonant circuits. So here if you can see, okay, the probe excitations. So here we'll be having the height B, okay, this one it is A and this one it is D. Okay, this is experiencing along the X direction, Y direction and Z direction. And similarly the loop excitation. Okay, so we'll have Y and X, the distance D, and here B. Okay, so that we are picturizing from here, we are projecting, okay, the loop excitation. Okay, so we'll have different cases. Okay, TM mode. Okay, so first case, the magnetic field along the Z direction, Z direction equal to 0. So neither M nor N would be equal to 0. So in this case, P, the value would be equal to 0. So we will be calculating the EZ value of XYZ. So E naught sine M pi by A X sine N pi by B Y cos P pi by Z D Z. Okay, and similarly EX. Okay, so that is minus 1 by H square. Same, M pi by A P pi by D, the cosine value. Okay, E naught cosine M pi by A X sine N pi by B Y sine P pi by D Z. Okay, and similarly Y direction. Okay, same, minus 1 by H square, but here since it's in the Y direction, it would be N pi by B P pi by D. Okay, right, E naught sine, first it will give sine, the value cosine sine. Okay, then similarly magnetic field. Okay, X Y Z. So it will be J omega by H square epsilon N pi by B E naught sine value cosine value cosine value, exactly opposite to what you saw in the electric field. And similarly HY value. Okay, HY value, it would be exactly what you saw in this value, this EY value. Okay, so it will be phase reversal, minus J omega epsilon by H square M pi by A E naught, here sine cosine M pi by A X sine N pi by B Y cosine P pi by D Z. Okay, so that the distance H square is equal to M pi by A the whole square plus N pi by B the whole square plus P pi by D the whole square. Okay, so we'll understand the dominant modes. Okay, so Hz value of XYZ. So H naught cosine M pi by A X cosine N pi by B Y sine P pi by D Z. Okay, so then we'll be calculating the EX value. Okay, so J omega mu by H square N pi by B H naught cosine M pi by A X sine value sine value. Similarly EY, it is phase reversal, minus J omega mu by H square H naught sine cosine sine. Okay, then the HX value would be exactly opposite of what you saw in the EX value. Okay, so minus 1 by H square M pi by A P pi by D H naught sine cosine cosine. Okay, and similarly HY value opposite, minus 1 by H square N pi by B, because this is Y. Okay, N pi by B P pi by D. Okay, so H naught cosine sine cosine. So both will be having the resonant frequency FR for the degenerate modes. So that would be equal to 1 by 2 square root of mu epsilon. Okay, M by A the whole square plus N by B the whole square plus P by D the whole square. So here 101, the TE101 is considered to be the dominant mode. Okay, so here A is greater than B, but it will be less than D. So here B lies between A and D. Okay, so we'll have the circular cavity resonators. Okay, so we'll have electric field lines and magnetic field lines. Okay, so we'll have the transverse section. Okay, the view. Okay, and afterwards if you put like this, okay, it's a longitudinal section. So maybe for the air filled circular cylindrical cavity resonator of maybe radius A and maybe length D, the resonant frequencies you can calculate. So 1 by 2 pi root of mu epsilon X Mn by A the whole square plus P pi by D the whole square. Okay, and similarly the transverse electric mode, it is 1 by 2 pi square root of mu epsilon X Mn by A the whole square plus P pi by D the whole square. So in this case J M dash of X Mn dash would be equal to 0. Okay, so in this case this 2D is greater than 2A, which is greater than D. So the dominant mode we already analyzed for TE 101, here TM010. Okay, so we will be calculating the EZ value C naught J naught, okay, of HR that you can substitute with the value, okay, the h value, and you will identify h5, okay, minus j c naught by eta naught j naught dash of hr, which is equal to this j c naught by eta naught j1 of that value 2.405 by a r. Okay, so the quality factor you are going to calculate q, the Tm mode for the dominant mode 010, it will be omega w by pl. Okay, so here we will be calculating 2we, okay, so that is epsilon naught by 2, okay, integral of ez square dv. Okay, so you are going to substitute. Okay, so here 2 pi by d, the limit varies from 0 to a. Okay, so j naught square, that value you'll going to substitute. Okay, so 2.405 by a r dr, so that you will be going for integration. So pi epsilon naught d, okay, c naught square, so a by 2 j1 square of 2.405. okay, so you will go on for evaluation of pl, okay, which is equal to pi a rs c naught square by eta naught square a plus d j1 square 2.405. okay, so this is the quality factor that you will analyze for the 010. So it is actually eta naught by the source resistance rs 2.405 by 2 multiplied by 1 plus a by d. Okay, so if you can calculate the resonant frequency, it will be 2.405 by 2 pi a square root of mu naught epsilon naught. So that you will try to substitute the value of d, okay, and you will get the value 0.115 divided by a multiplied by 10 power 9 hertz. So that is the resonant frequency for the dominant mode, okay, 0, 1, 0. So the basic configurations we will try to understand the coaxial resonators. The first thing, quarter wave coaxial cavity. Second one, half wave coaxial cavity. Third one, capacitance in coaxial cavity. So here the dominant mode depends on the dimensions of the cavity. As I told you, this d value is greater than a, which is greater than b. Okay, so here the dominant mode is TE101. But with the case of circular resonator, it depends on the dimensions of the cavity. Okay, so here this d would be lesser than 2a value, so the dominant mode would be equal to TM010. So we'll understand some problems with regards to the formulae what we have done for. Okay, so this is the question. A hollow cylindrical, circular cylindrical cavity resonator is to be constructed of copper. Okay, so here length d would be equal to 2a. Okay, so determine a and d for the resonant frequency of 10 gigahertz for the TM010. It's a dominant mode. Okay, also find the Q factor. Okay, so you know this FR. Okay, so from here I'm taking, okay, so 0.115 divided by a 10 power 9 hertz. So that one you are going to have the equation for the FR TM010, because it is given as TM010. Okay, so here this a value you are going to have 1.15. Okay, so that you'll calculate. Okay, so for example here if you can see, a and d is being asked for the resonant frequency of 10 gigahertz. Okay, so 10 gigahertz means 10 multiplied by 10 power 9. So that you can calculate the value of a. So here in place of that you will substitute 10 gigahertz. Okay, and you will find out the value of a. Okay, so it is, you can calculate 1.15 multiplied by 10 power minus 2 meter. Okay, right. And it's given that d is equal to 2a. So d is equal to 2 multiplied by this one. Okay, so d is equal to 2.30 into 10 power minus 2 meter or maybe centimeter. Okay, and similarly the rs value you can take again from the equation. You see square root of pi f mu naught by sigma. Okay, so pi f. Okay, what is that f? 10 giga value. Okay, you are going to substitute. Okay, 10 gigahertz. Okay, multiplied by 4 pi 10 power minus 7 divided by sigma. You are going to substitute 5.8 multiplied by 10 power 7. Again you are going to find out the value of rs, and you are going to have the q, because the q value is asked. Okay, so q is equal to 120 pi divided by this rs value. What is this rs value? 2.61 multiplied by 10 power minus 2. So you can substitute. You can substitute the value and get out the value of q factor. It is 11,580. Okay, so it's simple problems you can go for. So in the applications, as I told you, you can also you can also use it as a tuned LC circuit or maybe resonant transmission line. So, but naturally at much higher frequencies, they can be used for a better coverage like the waveguides. So they can be like input or maybe output tuned circuits of the amplifiers. So tuned circuits of the oscillators or maybe resonant circuits are used for filtering, or maybe it can be used in conjunction with the mixers. So in addition, they can be given shapes that can make them integral part of the microwave amplifying and oscillating devices, so that almost all devices will try to use them. Okay, so this is the application you can also use for cavity wave meter as well, so where you can better employ it as a microwave frequency measuring device. Okay, so as you know, it's a very simple cavity of cylindrical shape, so that insertion changes with the resonant frequency, and adjustment is done by means of the calibrated micrometer. So here the plunger has a absorbent material on one side to prevent oscillations in the back cavity, and micrometer is actually calibrated in terms of wavelength from which the frequency can be calculated. So here the signal is fed to the cavity wave meter through the input loop, and maybe a detector is connected to the output loop. Okay, so the size of the cavity is adjusted with the plunger until the indicator is going to indicate that pronounced oscillations are going to take place, whereby the frequency or maybe wavelength is read from the micrometer. So here coaxial line wave meters also is going to exist, okay, but they will be having a low Q factor than the cavity resonator. So maybe 5000, maybe you compare it with a value of 50,000. So same methods you can use it for coupling to the cavity resonators, that is actually employed with the waveguides. Okay, so various slots, loops, probes are used for good advantage when coupling of the power into or maybe out of cavity is actually required. Okay, so it must be realized. Okay, however, taking the output of the cavity not only loads but also it is going to change. It is going to vary with respect to resonant frequency, just like other tuned circuits. Okay, so maybe for a cavity that can be described as the insertion of the loop, which is going to distort the field that would have been existed in the resonator. So maybe a cavity may require retuning if maybe such a loop is inserted or maybe rotated to change the coupling degree. So you should know that one position of the loop, probe or maybe slot is capable of exciting several modes other than the desired one. So it's unlikely to be a problem in practice, however, because of the resonant frequencies corresponding to the spurious modes, okay, are hardly likely to be present in the injected signal. Okay, so here you can see the modulated electron beam. Okay, we have the gap, the beam direction. Okay, so we have the grids. Okay, so the electric field is taking in this direction in the resonator. Okay, so there is also one form of coupling which is unlikely with waveguides, but it's much more common with the cavity resonators, especially when used in conjunction with the klystrons. So this you can call it as the coupling to the electron beam. So here you will see a typical klystron activity together with the distribution or sum of the electric field. So maybe the beam is going to pass through the center of the cavity. So that is how the image will have the revolution about an axis coinciding with the center of the beam with the holes or maybe mesh at its narrow gap in order to allow the passage of the beam. So maybe if the cavity is actually oscillating, okay, so but the beam itself is unmodulated, having a uniform current density, then the presence of electric field across the gap in the cavity will be having that effect on the beam. Okay, so this field will be accelerating some electrons and will be retarding others. So that depends on the size and polarity of the gap voltage at the time when the electron is going to pass the gap. Okay, so if the current of the beam is maybe modulated and flows in pulses, so that the pulses will deliver energy to the cavity. So that will be having the oscillation if the pulse repetition rate corresponds to the FR value. So the same methods you can use it for the tuning the cavity resonators, okay, as you use it for the impedance matching with the adjustable screw or maybe post. That is the most popular way. Okay, so you have to examine the effects of the tuning and also loading. Okay, so that makes an impact on the bandwidth and of course the quality factor of the cavity resonator. Okay, so quality factor has the same meaning for the cavity resonators that you will use it for the tuned circuits. So Q is defined as the ratio of FR divided by bandwidth. Okay, so that's how you will understand the definition. So Q is equal to 2 pi multiplied by maximum energy stored per cycle divided by energy lost per cycle. So you can say that the energy is stored in the volume of the resonator and dissipated through its surface. So here we'll be having the shape which gives the highest volume to surface area ratio, that will be having the highest Q factor. Okay, everything being equal. So the sphere, cylinder, and of course the rectangular prism are used where high quality factor is the primary requirement. So maybe if the cavity is well designed, well constructed, and of course plated on the inside maybe with gold or maybe silver, its unloaded quality factor will range maybe from 2000 for the reentrant activity, maybe to 100,000 for the spherical one. So values would be like somewhat like more or less 40,000. So that is okay for the spherical activity when it is actually in the loaded condition. So maybe when the cavity is tuned by means of screw or maybe sliding piston, so here you will be having quality factor, and that should be taken into consideration.